Okay, we are going to get started with looking at characteristics of rational functions. I have two rational functions here. Right now they are overlapped and we're going to look at them separately. But notice the difference of them. The first one that we're going to look at has the x squared in the numerator. The second one has x squared plus 3x minus 10 in the denominator. And notice the x plus 1 is also flipped positions. Okay, so remember what a rational function is. It is a function where it is a fraction of polynomials. So all last chapter we studied polynomial functions, and now this chapter we're starting off with rational functions, which means we have a polynomial in our numerator and a polynomial in our denominator. So what we're going to look at today is just some characteristics of polynomial functions and how flipping them. So the first one has the x squared plus 3x minus 10 in the numerator, how putting that in the denominator changes our graph. Because if you look here, you can see the graphs are completely different. But we want to talk about and learn about what parts of our rational function kind of help us with our x-intercepts, our y-intercepts, and what we call asymptotes. Okay? So the first characteristic we're going to look at with rational functions are the roots of our function. And your roots come from when your function is equal to 0, okay? Notice this first one, our roots are -5 and 2. I plotted them when I graphed it. And if you look at the second one, you only have one root, and it is -1. Okay, so you might be thinking, what gave us these roots? Okay, we know a root or a solution happens when our function equals 0. So if you think about if you did set your function equal to 0, let's say this one right here, x squared plus 3x minus 10 all over x plus 1 equal to 0, and you tried solving that, you would cross multiply. And you would get x squared plus 3x minus 10 equals 0. And we would continue to solve. We have a quadratic. And our two factors of -10 that add up to +3 are 5 and -2. And when we solve those, we get -5 and 2. So notice how we got our roots by setting that equal to 0. Let's look down here. If we set this one equal to 0, and solve. And I cross multiply. 0 times anything is 0. And notice your only solution here is -1. So look, when you cross multiply, 0 times anything is just 0. So the shortcut here for finding roots of a rational function is just setting your numerator equal to 0. Okay, so notice in the first one, our roots came from our zeros of the quadratic x squared plus 3x minus 10. And in the second one, our zeros came from our zeros of our numerator of x plus 1. So it's important to kind of know that shortcut for your roots. And we'll put a little note here. To find your roots, set your numerator equal to 0. Okay, so we did that. Now, something else that we want to look at is we have what's called a vertical asymptote. And vertical asymptotes come from where our function is undefined. Now, your graph doesn't graph them, but we will be graphing them. And so I'm going to put this one in here. And it's at the line x equals -1. It's a vertical line. And what it means is your graph, as it approaches it from the left, like as your x values get closer to -1 from the left, that graph goes up to infinity. As it approaches it from the right, it goes down to negative infinity. Your graph will never cross a vertical asymptote, okay? Ever, ever, ever. So now here, notice where our graph starts to go up to infinity. Right here at -5. And at +2, okay? So if you're thinking, okay, those values seem familiar, they are. Notice what they are. They're your roots of your denominator, right? Because if you think about it, what makes a function undefined? When your denominator is 0, we can't divide by 0. That is undefined. So to find what we call our vertical asymptote, and it's really important to make sure that you write your vertical asymptote as the equation of a line, you set your denominator equal to 0. So if you look at this first one, we set x plus 1 equal to 0 and solve. So your vertical asymptote is x equals -1. Down here, we set that quadratic equal to 0. Well, guess what? We already solved it up top. And x equals -5 and 2. Now notice that I do write those as an equation because it is an equation of a line. My roots are not a line, right? Those are just the x values that make our function equal to 0. Vertical asymptotes are an equation of a line. Our vertical asymptotes actually also help us with finding our domain. So if we look at this first one, notice that we're coming over, far from the left. All x values have a point, except at our vertical asymptote. And then again, all x values have a point, except that -1. So your vertical asymptote helps you with your domain because your domain is all the values where the function is defined. So we would say it's defined from -infinity to -1, union -1 to infinity. Down here, notice that coming from the left, it's all the values until we reach -5. And then all the values until we reach 2, x equals 2. And then all the values until it goes to infinity. So your domain of that one is all values except -5 and 2. We have to write that in interval notation. And it's okay, we have 3 intervals. Another important piece about graphing rational functions is recognizing where it changes sign. So notice here, I will choose a different color. Maybe I'll do purple. So notice here, as we scroll through here, our outputs are negative. It changes sign and goes to positive at an x-intercept, right? And then it's positive, 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 positive. When does it change sign? At the vertical asymptote. And now all our function values are negative. And then again, we get to that x-intercept, and now it's positive. So it's important to notice that your function value will change signs, and that means going from negative to positive, or positive to negative, or negative to positive at vertical asymptotes and x-intercepts. They might not always change at the vertical asymptotes, but if it's going to change, it'll change at a vertical asymptote or an x-intercept. And we can see that happen on this bottom one too. Notice here, all our outputs are negative, 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 negative outputs. Vertical asymptotes, right, changes to positive. Then we have all positive outputs until it reaches that x-intercept, and then we have negative outputs. So notice how it goes from positive to negative again. And then at that vertical asymptote is where it changes from negative outputs to positive outputs. Why is it important to recognize that? Because it's just going to help you with the overall graph, okay? I started these problems by giving you the graph. We're going to get into graphing them, and we're going to need to know kind of, what the shape looks like without always relying on our graphing calculator. The last thing we're going to look at quickly is just your y-intercept. When we look at our y-intercept, remember that it's where your x value is 0. So kind of the easiest thing to do is if you're looking at your equation, it's almost just get rid of all your x's. Not you're getting rid of them, we're just ignoring them. And looking at this coefficient right here. Because if you plugged in 0 here and 0 here and 0 here, you would be left with negative 10 over 1. And that would give you a y-intercept of 0, comma, negative 10, right? And on this graph, it's hard to see because I didn't get it all. 6, 7, 8, 9, 10. It would be right about here. And your graph would be going through that, which would be 0, negative 10. If you look on this side, if you plug in 0, 0, 0, those all are gone. And you're left with 1 over negative 10. So that's going to be your point, 0, comma, negative 0.1. And notice that is highlighted here on our graph. Okay, so to get your y-intercept, we've been doing that for a long time. We plug in 0 for x and solve. So with rational functions, the easiest thing to look for and the most time efficient is looking at your ratio of your coefficients. Because when we plug in 0 for x squared or for x, doesn't matter the coefficient, those zero out. The only time it won't change is when you have just a constant, right? Negative 10, doesn't matter that x is 0, it's still negative 10. 1, doesn't matter that x is 0, it's still 1. Okay? So you guys have assignment 2, and we will continue to look at characteristics of rational functions tomorrow. Have a good day.